Let's revisit an idea we've already discussed in a previous section, matrix transformations. So let A be an m by n matrix, m rows, n columns. We're going to define transformation T from Rn to Rm by the matrix multiplication of the input vector. So T of V is just matrix A times vector V. This is a matrix transformation, and we saw in the previous section that matrix transformations are linear. So this transformation T would be a linear transformation. Okay, so let's do an example with it. So let's let T be a linear transformation from Rn to Rm induced by matrix A. So what does that mean? It means that that T of an input vector is just matrix A times vector X. That's what it means for a transformation to be induced by a particular matrix. We just take any input vector we have and multiply or left multiply the input vector by the matrix. Okay, so I need to find a few things. I need to find n and I need to find m. Then I want to find the image of my vector space T. Okay, so n and m are the dimensions of my vector spaces. Okay, Rn and Rm. So what's going to make sense here? So my input vector should be n-dimensional. Okay, so x should be n-dimensional. So x should be an n by 1 vector. Right? So x is an n by 1 vector, an n by 1 matrix. N rows, 1 column. A, we can see right here, is a 3 by 2 matrix, 3 rows, 2 columns. Okay, the result, once I put them together, should be in the codomain, which is Rm. That means it needs to be an m by 1 vector, m rows, 1 column. It's a column vector with m components. Okay, so using this, we can use what we know about matrix multiplication to figure out what n and m are. All right, in order for the matrix multiplication here to work, in order for it to be well defined, we need the number of columns of A to equal to the number of rows of vector X. Okay, so since A has 2 columns, vector X better have 2 rows. Otherwise, the matrix multiplication would not be defined. Okay, and we also know when I multiply 2 matrices together, the resulting output matrix has the number of rows of the first matrix and the number of columns of the second matrix. So m by 1 better be 3 by 1. That means m better be 3. Okay, so for part A, n has to be 2, m has to be 3 in order for the matrix multiplication to make sense. Okay, based on our current matrix A. Notice that means A is a 3 by 2 matrix, so the number of columns of a transformation induced by a matrix, or the number of columns of A, is the dimension of the domain of the linear transformation induced by that matrix. Okay, A has 3 rows here. The dimension of the codomain is going to be equal to the number of rows of the matrix that induces the transformation. Okay, so we found n and m. We want to find the image of T. The image of a transformation or a function is just the space that we map to. Okay, we know our transformation in this case maps R2 into R3, but does it map into all of R3, or is it just some subset? The image is the actual exact set we map into. Okay? So to understand this, we're going to kind of think what the transformation does. So I'm going to plug in a particular vector, which I know must be two-dimensional. So let's imagine we plug in a vector with components A and B. Then to apply the transformation, we want to multiply that vector on the left by matrix A. Matrix A is, what was it, 2, 1, 0, 0, 4, 1. So first column 2, 1, 0, second column 0, 4, 1. Times the input vector AB. Okay, and we can see that from what we know of matrix multiplication, we can write this as a linear combination, A times the first column of the matrix plus B times the second column of the matrix. Okay? Now, there's nothing special about A, B. I could plug in any value I want for A, any value I want for B. This will still hold. Right? So actually, the transformation is going to be just the set of all possible linear combinations of these two vectors, where the vectors are the columns of my matrix. Okay? So the image of T is just going to be the span of the columns of A. We also call that the column space of the matrix, right? So for a transformation induced by a matrix, the image of the transformation, the space that the outputs actually go to, is going to be equal to the column space of the matrix. Okay? In this case, the two columns of the matrix, you could see pretty quickly just eyeballing it, are linearly independent. And so they form a basis for the column space. So if I have a two-dimensional vector space, that's going to be a plane. So the image of T is going to be a plane in R3. All right, so that's the actual space within my codomain that I actually map to. Every vector from R2 maps to R3, but only into a plane of R3. Doesn't have to map to fill up all of R3, right? You don't have to fill up your entire codomain.